So, welcome back to the second session of the day 2 of EasySpin Academy 2020. In the previous session, we looked at some basic least squares fitting using the EasySpin function ESFit. We looked through all the basics of the interface. If you have any questions, please post them in Slido, and the link is provided on the website. People will answer it there, or you can also keep your question upvoted, and might be addressed also in a Q&A session that happens after the end of our all sessions today. Finally, if your question is still not answered, come over to the happy hour and track one of the EasySpin folks down to answer your question. The happy hour happens at gather.town, and the link is also provided on the website. So with this now, in the second session, let's look at some more structured spectra and appreciate the difficulties one can get when trying to fit them. We'll also look at multi-component fits and how to use the command line. So let's first start out with getting a highly structured spectrum. So we're going to clear everything out as usually. Then we're going to load a data file called radical.dta. These data files are included in the zip file we've provided to you. So you can, after the workshop, you can retrace all what we're doing here. Let's go look at the spectrum. Well, here it is. This is a radical spectrum with a ton of lines. Whenever you have a spectrum with a lot of lines, it means that you will have a lot of minima in the area surface, and the fit is going to be very difficult if you don't do some pre-analysis. Let's see how that works. So microwave frequency, I think was 9.5, and the range we're going to, again, as previously, just copy from the experiment. Field vector with the minimum and the maximum from the field vector defining the edges. Okay, starting system z0.nukes is, we have 2 protons now. We know that from the molecular structure, and we know that we've got 5 of the first type and 3 of the second type. Should be cis0. Then we've also going to add the G value, which we know is 2, and the hyperfine value, which we guess is 20 and 8, and cis0 some broadening, and it looks like more a Lorentzian type broadening. So we're going to start out with 0 Gaussian broadening, which is the first number in LWPP, and 0.02 millitesla in the Lorentzian broadening. As usual, if possible, just annotate your code with the right units so you don't mess up later. Okay, now we're going to ESFit. This is a solution spectrum of an organic radical, and the EasySpin function to simulate solution spectra is called garlic. So we're going to use @garlic. Then we have to supply the spectral data vector, SPC. The starting system, cis0. Then we'll also need a vary structure, so basically tell ESFit how much it can vary each parameter. And let's call that just vary.g. The G value needs a little bit of adjustment from 2.000. We're not quite sure about these hyperfine couplings, so let's vary each of them by ±4 megahertz. And we don't quite know the line width either, but we limit ourselves to Gaussian, to Lorentzians right now. So let the line width vary by ±0.15, again in millitesla. Okay, so we provide this vary structure, and then we provide the experiment. All right, so this, what did we do? We loaded the data, we defined the experimental parameters, we defined the spin system with some initial parameter values or estimates that we read off from the spectrum, and then we give the range over which ESFit should vary these parameters. Now Control-Enter will bring up the fitting interface again. And now you see we have 4 parameters that are being varied. There is no limit, no built-in limit on ESFit of how many parameters it can handle. But the fact is that if you have more than maybe 5 or 6 parameters, the fit gets very difficult because the parameters surface is very high dimensional. In those, if you have a lot of unknown parameters, I recommend fitting separate subsets of parameters iteratively. For example, if you have 6 parameters, fit them 3 and 3, and It will require some work to figure it out. ESFit is not a magic bullet, it's a tool for you to find the global minimum. And it can be very hard if the error landscape is extremely ragged and has a lot of minima, like an egg carton. All right, let's just do a simple thing. Click the start button. And you can see with red, as usual, the current simulation, and in green, you can see the current best fit. And it seems like it got to some sort of local minimum because it's not exploring much anymore. It's just, and the RMSD is not decreasing much anymore, so it's probably just finalizing its fit in this particular local minimum. But then if you look over how bad the RMSD is and how bad the fit is, you see that this is definitely not your global minimum. The trouble here is that some of the simulated line positions are spot on, like this here, or this here, or this here. And also in here, there's some that fit really nicely, here and here. But the fit is only partial. But it's good enough partially that this forms a local minimum in the error surface. And as a local minimum, these local search methods have no way of getting out of that local minimum. So for these cases, it's not good to use a local search method with the integral and try to fit it. So you can try a more global method. And the dumbest global method is Monte Carlo, which just randomly generates some parameter sets and simulates the spectra. You know, as somebody sometimes at some point said, running Monte Carlo is usually means there's a smarter way of doing it. So now actually we had a crash because we probably ran out. We hit 0 in the lower limit. I think we have to start ESFit again and maybe reduce. There we go. So the trouble was that our lower limit of the blind broadening is smaller than the field increment. This will lead to a crash. So let's see if we can increase that a bit and get out of that trouble zone. So let's do Monte Carlo again and run this fit again. And now you can see in the root mean square deviation plot that there is no systematic lowering happening because this algorithm doesn't systematically walk down to a local minimum with on the error surface. It just randomly looks at random points. It's just somebody flying all over the Earth to find the global minimum. And as you can see, it's making very little progress. All right, so again, this is very challenging because the algorithm doesn't use any information from the error surface to find a minimum. It just hops around like crazy. Sometimes it's lucky and it finds a reasonable fit, but in general, Monte Carlo is not very effective. On the other hand, you can use something like a genetic algorithm or grid search or particle swarm to see if that helps you find a local minimum much more easily. And any of these methods will now take a while to explore the full surface. As you see, we got one relatively low hit here on the logarithm of RMSD, so 0.08. But I won't let this run now forever. What you can also try to do, since these are many lines, you could try to fit the Fourier transform. That could potentially be better. It might not be. But basically all you need to do is just really try around and see how well your fit gets and if you get any better. As you can see, the spectrum is shifting around a lot, which might indicate where our G value range is a little bit too large, so it might be worthwhile to narrow down these ranges. In general, if you want to achieve a good fit, you have to have three important things. You have to have good signal to noise in your data, right? Second, you have to have a good starting point. The closer your starting point is to the actual fit parameters, the better, the more easily you will find it. So for example, if you're looking for the Dead Sea minimum in Israel/Jordan, it's better to be in the Middle East than to be in South America. And third, you need to make sure that your search boxes, your search boundary constraints are as narrow as possible. So don't look for g-values between 1 and 3 for this particular spectrum, but only between 2.000 and 2.005 maybe. So for these three things, just good data, good starting point, narrow search range, it means you have to do some pre-fitting analysis. And for organic radicals, it's actually easy to do because you can just measure the distance of splitting between the outermost two peaks. And that fixes one of the hyperfine couplings. So you can fix that one hyperfine coupling and narrow its search range quite a lot. Okay. So let's maybe say I know this and I've read this off somewhere. So I'm gonna reduce the search range here to 17. And I'm also gonna reduce the search range of the G value to 2.000 to 2.003. Okay. And we still have some uncertainty here. And let's say I've managed to identify to get a little tighter with this. And now if you start, you will see that we should get a much more successful fit. It will still take a while, but we're now searching a much smaller range, which gives a much higher chance of success. But typically, least squares fitting is not something that is a black box thing where you just click start and it fits it for you. You need to have good data, you have to have a good starting point, and you have to have a narrow search range. And only in those cases will you be successful in fitting it. So hopefully these are gives you an idea of how difficult fitting can be, even with a good tool like ESFit. So next, I'd like to demonstrate you how to simulate or fit a multi-component spectrum. Okay, I'm gonna load now. I'm gonna clear everything. I can actually probably delete this here. Clear everything. I'm gonna load some prepared data from a file called NX2, which represents a mixture of two different nitroxide radicals with different mobilities actually. Exp.mrefrec equals 9.5. As before, we also have a field range, which is going to be the minimum of B and the maximum of B. Now let's define a spin system. Nitroxide radical has a full G tensor of 2.085, 2.065, 2.03, 2.03. Let's say we have a 14N nucleus, and the hyperfine coupling is maybe roughly 20, and 95 megahertz. Again, in a G tensor here you specify Gx, which is along the x direction of the tensor, Gy, and Gc. And then for A, we also have the Ax value, the Ay value, and the Az value. And since we didn't specify any tilts of tensors, all these tensors are collinear and are aligned with the molecular reference frame. We're going to add some phenomenological broadening, let it be Gaussian of 0.2 millitesla, full width at half max. Now, we're going to make two nitroxide radicals. I'm going to just copy these over. NX2 equals NX. And what all of this does, it just takes the variable NX and duplicates it to a variable called NX1. That's going to be our first radical. And we're going to do the same thing and copy it over to NX2 to make the second radical. Now we're going to add correlation times, and we'll talk about this more in the next session. So bear with me if you don't quite understand this yet. But it's just another simulation parameter to characterize the mobility of a nitroxide spin label as it moves in solution. We're taking the logarithm of the correlation time, which is let's start with -9 for the first radical, and let's say -8 for the second radical. And as we had seen yesterday, if you have a mixture of several spins, you have to specify what the relative concentration is, and you can do this with a field called dot weight. And we can start out with, a 50% 50-50 mixture. Okay, let's first plot the spectrum, go look at it. Here's the spectrum. You can see there's some noise. Then we see, if you're familiar with nitroxide spectrum, you will see there's these 3 sharp peaks, 1, 2, 3, that correspond to come from a nitroxide radical that's actually moving fairly quickly in solution, tumbling very quickly. And then you see these broad features at low field here, and then the high broad featured high field that goes all the way up here. And that is due to a nitroxide radical that's less mobile. And this is very typical of, let's see, a nitroxide spin label protein where you haven't been able to completely separate out like some free spin label reagent and that's still in solution. So your EPR sample will contain nitroxide either attached to the protein where it's less mobile and gives a broad spectrum, or still free in solution where it's much more mobile and will give these 3 sharp lines. You can now, with EasySpin, you can just simulate both components at the same time. And you don't, you can still make use of this spectrum even though it's contaminated by the free radical. Okay, what do we want to vary in the fit? Well, we definitely want to vary the weights, right? And we're gonna make it plus minus 0.45. And for both of them, so vary 1 and vary 2. We have, since we now have 2 spin systems, we'll also have to have like 2 vary structures. We might also want to vary the correlation times, so log T core by half a decade, each of them, vary 1 and vary 2, also vary half a decade. And finally, you know, we might not entirely be sure about this third hyperfine value of 95 megahertz. This is one that really affects the X-band EPR spectrum quite a bit, so it might be wise to include that in the fit as well. So just A3 can be varied by plus minus 10, both for the first radical and the second radical. So as you can see, we have 1, 2, 3, 4, 5, 6 fitting parameters. Let's call ESFit. Our model function now is Chili, which we're going to talk about in the next session. That is the function that allows you to model motional EPR spectra. We again have to feed the data, SBC, and now we have to supply both spin systems at the same time, right? And as we saw yesterday, you need to do that by writing curly braces and then write NX1, NX2. So this just tells us that the sample contains 2 spin systems. Then we also have to supply the 2 vary structures, vary 1 and vary 2, instructing ESFit on what can be varied in each of the spin systems. And finally, the experiment. And if you run this now, you will get this interface. You will see that there is, there is the spectrum here. We have these 6 parameters. And if you want, you can just click start, but that might not be a good approach. It might take way too long to get anything fitted. And you can see we're completely off. You can see a little tail here at the lower edge, right? So which basically indicates that something is wrong. We might have the wrong frequency. We might have some wrong starting values. And I need to press stop here and go back check what's going on. I think our trouble here is with the G value. We put this 2.08 in, which is just missing a 0. So we just screwed up with the starting values. Now, if you start this again, you see that overall our starting values aren't too bad. Now, this peak is still not fitted. The intensities are not right. But, it's pretty hopeful. We're fairly close already. And as you can see, we seem to be lucky getting towards something that's looking better. Still having trouble to figure out the width of this peak. That has to do with the correlation time. We can now, for example, press stop. And then we can save the parameter set. And then switch to Levenberg-Marquardt, which is the fastest fitting algorithm. That gets you to the local minimum fastest. Start fitting and see if that helps. Stop. I have to start from the, not from the center of range. I actually have to start from this parameter set. in the selected parameter set. There you go. Start. And now you see it's actually starting from where I wanted to start. It's already running simulations. Initially, sometimes it has to do 5 or 6 simulations to get the lay of the land before the fitting algorithm starts descending down to the local minimum. And as you can see, the Levenberg market is actually stuck here. It can't get out. So you probably have to go back and start the Nelder-Mead simplex, which is a little less likely to get stuck, and see if that gets you further down to the minimum. And as you can see, it's slowly able to walk out of this minimum. This line gets better. We're not going to wait here for the final fit to finish. But the bottom line here is that you can fit a 2-component spectra. You could now deactivate some of these parameters, fit the others first, and then invert that around. That's often also a good strategy. I could, for example, stop this now, deselect everything, and now just fit the correlation times and see how that goes. Are we able to get a better fit for this spectrum here? It doesn't look like it's helping us a lot. So just feeding those 2 parameters doesn't work because some of the other parameters are still off. So as you can see, this is an iterative procedure that really requires you to think about your spectrum as well. Let's click stop here and close. So this is how you fit a multi-component spectrum. Finally, I'd like to show you how to do a command line call for ESFit. So you can do the exact same fit by, instead of just writing ESFit, you could ask ESFit to return you the fitted spin systems, the fitted spectrum, and the residuals with an equal sign. So basically, you just prepend your ESFit call with this. And if you do this, it will not start the graphical user interface. It will just start running. And then when it's done, you can basically just plot the spectra. You can also now add some fit options. So ESFit right now takes the function, the data, the spin systems, starting values, the parameter variation ranges, the simulation experiment parameters. Then there could be some experiment options, like, for example, the number of knots, as we've seen yesterday, might need to be changed. And finally, I think this is the 1, 2, 3, 4, 5, 6, 7th input to ESFit are the fit options. All these things you can change on the interface, and many more are actually settable explicitly here via these fitting options. And I'm going to just show you a few examples. So fit opt .method, you could specify that you want to do Monte Carlo. Just type Monte Carlo. Or you might want to specify Levenberg Marquardt, and then you say levmar. In this string of method here, you can also specify whether you want to fit the function itself, or the integral, or the double integral, or the Fourier transform. This is called the target, and you can just type int for the integral. We also talked about the scaling that needs to happen in order to match a simulation to an experiment. And you can set that scaling with fitup.scaling. And I think what we used is we used least square scaling of the amplitudes, LSQ. If you want to include a shift, you say LSQ 0. And sometimes, since you can't hit the stop button when you want, but let's say you do want to just run this for a couple of hours and see what the best fit comes out, what you can do is says fitup.maxtime equals, let's say, 120. This is in minutes. So ESFit will just run for 120 minutes and then just give you whatever is best at that point, which doesn't mean it's the fit, but it allows you to look at it and maybe restart it with a different fitting method or a different scaling. So you can make it kind of time out. So this kind of concludes a brief overview of ESFit, of how you can use it interactively, how you can use fit multi-component spectra, and how you can use it from the command line. We'll have one more fitting session today where we talk about custom fitting functions, which are an extremely powerful tool to adjust what you're fitting and how you're fitting. But before that, in the next 2 sessions, we talk about slow motion EPR and rapid scan EPR. It's now 8:35. We have 5 more minutes in this session, where I encourage you to just look at the script with ESFit and maybe also browse the documentation. If you go to the documentation locally, you will find there is a user guide on least squares fitting, shown here. And there is the function reference for ESFit, which is on this side. And if you click on the function reference, you will see that all these fit options, fit up method and fit up scaling, are documented. There's also some other fitting options. Fit up also takes, you can fine tune each of the fitting algorithms through these fit options as well. So for example, Nelder downhill simplex, you can set some algorithm specific things like the function tolerance, the tolerance on the edge length, the simplex parameters, and so on. Also for Levenbach-Markert, Monte Carlo, genetic algorithm, grid search, and particle swarm. So if you use the command line, you have full control over these algorithms, which you don't have in the graphical user interface. So check out the documentation, and I will see you back in about 14 minutes for the next session, which will be on slow motion CW EPR.